So today we're looking at section 11.2, and this is infinite series. So you look at sequences, which is where you just had the terms, and you would decide, remember you could decide whether the term converged or diverged, and you played with that. Now what we're going to do is we're going to look at a series in the sequence, and it'll be a series because we'll be adding them. We'll look at what we call partial sums, like if we added the first 5 terms of a sequence, that would be the 5th partial sum, and it's a series where you add it up. And it actually turns out later on that we'll look at the sum of the series, you know, the big, like the 5th series and the 4th and the 3rd. So like we'll say S sub 5 would be the sum of the first 5 terms, and S sub 6 would be the sum of the first 6 terms, and then it's that sum, that each of those answers, S sub 5, S sub 6, those could be also a new sequence, a sequence of sums. Okay, so you kind of extending out. But let's look at some patterns in this, and we're going to do some fun. You'll see one series called the geometric series, which is really interesting. I don't know how much time you spent worrying about how to write a repeated decimal as a fraction. You know, like 0.33333, you probably know is 1/3, or 0.666 is 2/3, and 0.11111, you might know, like I know that's 1/9. But anyway, any repeating, like what if it was 0.256, 256, 256? Well, you know that that is rational because it repeats. There must be a fraction, but to figure out what that fraction is, you actually use the techniques of you write it as a geometric series, and then you can describe it. So that's kind of a fun little activity that we'll do at the end of the lesson. So I will go to the document camera, and we will start looking at these, not document camera, laptop, and look at these sums. So this is section 11.2, and here we are. We have our first, second, third, all the way into our nth partial sum. And so the first term of this, or the first sum is 1, and then S sub 2 is the first term of the sequence, so it's 1 plus 1/2. So it must be that the sequence itself is 1 over 2 to the n minus 1. This is A sub n. And so that's why the first term was 1 minus 1 is 0. 1 over 2 to the 0 is just going to be 1. And so y'all getting the idea? Okay. And so then this is the pattern. And then they say, this is, like, for me, this is where it's kind of tricky. They just kind of, looking at this after a while, they realize that they could say, well, this is like 2 minus 1. This adds to 3 halves. So this is 2 minus 1/2 is a way to think of that. Now this adds to 7/4, which is 2 minus 1/4. So I guess what I'm saying here is I would definitely go to this first before I would see this pattern. So to me, when they put this out here, you're like, well, how did they know that? Well, I'm thinking that perhaps you might be able to reason out. I don't even know if you would be able to reason out that you do 2 to the n minus 1 over 2 to the n minus 1. Or 2 to the n minus 1 over 2 to the n minus 1. But I think what would happen is you would start to see this pattern, and then you would recognize that you could write this as 2 to the n over 2 to the n minus 1 over 2 to the n minus 1. And then this is 2 to the n minus 1 over 2 to the n. Well, that's just 2, because this is like 2 to the 5th over 2 to the 4th. It simplifies to just 2. So that's where they get the 2 to the 1 minus 2 to the n minus 1. But that could be, to me, a little tricky. But what this is telling you is that as this series goes to infinity, as n goes to infinity, this series actually sums to 2. Okay? So what they're telling you is if you were to look at this as the lengths, if you add 1 plus 1/2 plus 1/4 plus 1/8, plus 1/16, if you add those up one by one, that sum eventually gets to 2. So that's kind of interesting and maybe not intuitive. 1 plus a half plus a fourth plus a eighth plus a 16th. And then eventually. But visually, you can kind of see how that feels like it would make this, especially this part would be going to, from 1 to 2, that's going to 1. So you can kind of see how. Okay. All right, so we're going to talk about a definition here of the infinite series. Make this a little bit bigger. If you're given a sequence of numbers, a sub n, and here's your expression, what you're just going to do is you're going to add them together, add each of the terms, and that's called an infinite series. The number a sub n is the nth term of the series, and the sequence, so we now have a sequence, s sub n, is defined as the sequence of what we call partial sums of the series. The number s sub n being the nth partial sum. So like s sub 4 would be the first 4 terms of the sequence. S sub 8 would be the first 8 terms of the sequence. And then you think about these sums of sequences themselves as a series. Okay, or as a sequence of partial sums. And it says, if the sequence of partial sums converges to a limit L, we say that the series converges and that its sum is L. In this case, we also write, a sub 1 plus a sub 2 plus all the way down to a sub n is equal to the sum as n goes from 1 to infinity, a sub n is equal to L. So this notation, summation notation, you've seen when we looked at Riemann sums. So if the sequence of partial sums of the series does not converge, then we say that the series diverges. Okay. Now, a really fun first series that you're going to look at, and it's kind of one that you want to be familiar with, is called the geometric series. So I'm going to put some notes inside here before I give you that formal definition that I copied from the notes. Okay, so say we have a series that looks like this. You have A plus A times R plus A times R squared plus, you keep going, A times R to the n minus 1, and then you keep going until infinity. And so we could describe this as the series, as the sequence, or the sum from n goes from 1 to infinity of a r to the n minus 1. And a and r are real numbers, and they're fixed. And of course, we don't want a to be equal to 0 because that's kind of dumb. Then you could have this ratio r, it can either be positive or negative. It's just some number. Now, let's kind of think about it. If r was equal to 1, then the nth partial sum, IA, sum of the series would be, well, if r was 1, it's not going to be very exciting, right? You're going to have a plus a times 1 plus a times 1 squared plus, continuing on, a times 1 to the n minus 1. So what do you end up with? Well, how many a's do you have? You have n of them. So if you add them all up, you just have n times a. And so if you let n go to infinity, clearly this series is going to go to infinity, and so it diverges. So the series diverges because the limit as n goes to infinity of S sub n, remember S sub n, you consider the partial sum, is also going to go to infinity. So we say,
That as long as a is greater than 1.
well, yeah, it could be that a is negative, and then it would go to negative infinity. Is that what you mean?
I guess as long as a is not a fraction.
Well, even if a is a fraction, a is just being added over and over again. So you're just adding a fraction. I'm not raising the a to the power. You're thinking about r. Yeah, and you've already seen this, obviously. So you're excited about when r is a fraction between -1 and 1. We do have a convergence series, and that's what I'm going to get to in just a second. Okay. So now if r, okay, so if r is equal to 1, that happens. If r is equal to -1, what happens is that the series diverges. Let's see if we can see why. Because what would happen? Let's see. Let's consider what would happen. If you had S sub 1, of course, would just be A. S sub 2 would be A times -1, A plus A times -1, right? And S sub 3 would be these ones, A plus A times -1 plus A times -1 squared, right? And S sub 4 would be all of these So what would that be equal to? Can you tell me what these, can you see what these are equal to? What's this? This one's just A. What's this one? A plus -A. 0. What's this one? A. Okay, and then this one is 0, right? So what's happening is the series, each of the terms of the series, right, or the partial sums are alternating between either A or 0. So and so that where we would have to say that the series diverges for that reason, because if you know, you're bouncing back and forth. You're not getting one particular number that it's closing in on. Okay, so the nth partial sum sums alternate between A and 0. Okay? Now, if R is not equal to 1...
Your conference is scheduled to end in 2 minutes.
Let's think about it. Now, and we have to be kind of clever, because what's going to happen is it really depends whether, if R were 5, you could probably argue to yourself that it's going to do what? If R were 5, what do you think the series would do? If we had 5s in here, like this would be, yeah, it would diverge. It would diverge if R were 5, because you'd have A and then 5A and then A plus 5A plus 25A. I mean, it would just be growing without bound, and so it would diverge. The series would diverge. So let's just think about the series, or the partial sum. S sub n is the first term plus the second term plus the third term plus, and you continue that pattern, A times R to the n minus 1. Okay, so that's the pattern for the nth partial sum. Now, just for fun, and this is just being clever, but just for fun, let's multiply both sides of this equation by R. So I'm going to say R times S sub n equals And this will be a times r plus ar squared plus ar cubed plus continuing on, and this will be a times what? R to the n. Okay, so this is just a little trick. So we just multiply both
Your conference is now over. Goodbye.
by r. Are you still there, Brandon, or did you leave?
Still here.
Okay, so I don't know, that woman needs to go away. All right, so she's been here all semester. So this was just a little trick that, somebody smarter than us came up with. And then what they do is they say, okay, what I'm going to do is I'm going to, it's kind of a real common thing, but anyway, I'm going to subtract r sub s sub n from s sub n. Okay, so I'm going to do s sub n minus r s sub n, just for fun. Okay, and I'm going to see what happens. So do you guys see how this AR and AR will cancel, and AR squared and AR squared will cancel, and then the AR cubed and AR cubed would cancel. And this would cancel also, and all that would be left is the first term, which is A, and then this last term, which is A times R to the N. Right? And then if I wanted to be clever, I could, because remember the whole idea is I'm trying to see if I could describe this, find a pattern for the sum. So like up here, here I kind of gave you this one and I showed you the pattern. We kind of came up with a pattern for the partial sum. So that's what I'm trying to do. So if I'm trying to get a pattern for the partial sum, then I might want to isolate the partial sum by factoring it out. And I'll get 1 minus r here. And then if I wanted to be clever here, I could do the same thing and factor out the a. Okay? And then I can actually solve this for s sub n. And I get s sub n is equal to a times 1 plus r to the n over 1 minus r. Wasn't that cool? Okay. I know. Well, the reason you have a hard time following it is because I was extremely clever right here when I decided to multiply everything by r. And what I'm doing is I'm giving you the rationale for how you can find the sum of a geometric series. Because it turns out, and it may have been better if I had just defined it first and then given you the proof. I kind of proved it first and then didn't give it to you. But it turns out that if you have a geometric series, this sum is equal to a over 1 minus r whenever your r is less than 1. And you can argue that because we just found a clever way to describe the partial sum. I mean, do you agree with what I did? It's at least legal, right? I multiplied everything by r. That's legal. And then I subtracted these two statements, which is also legal.
That's what I did.
This was just being clever, again, for fun. Subtract r s sub n from s sub n. And the reason we did that is because we wanted to try and see if we could find a way to describe s sub n without all these dots in it. So I didn't have to do all that work. Okay? And so then I got some stuff in the middle to cancel out, and I just ended up with the first term and the last term as equal to this. And now I'm able to actually factor s sub n out, and now I can describe s sub n in a better way. I mean, here it's described, but this way is a lot less work. It seems a lot less, not as much to work with or worry about. Okay. Now, what happens is if r is greater than 1, this is going to grow without bound. As n goes to infinity, this is just going to be really big, right? And so if r is less than 1, then what happens is this, like say r is between -1 and 1, this will be like a half or a third or something like this. This will go to 0, right? So at the limit, as n goes to infinity, when r, let me change it to black. Let's see. So if the absolute value of r is less than 1, the limit as n goes to infinity of s sub n will just be, well, this will go to 0, so you'll just get a over 1 minus r. And that is what the series converges to. And obviously, if the absolute value of r is greater than 1, the series diverges. Because this will go to infinity. The limit as n goes to infinity of s sub n will go to infinity. Okay, so what that tells us then is that if the absolute value of 1 is, or the absolute value of r is less than 1, which means r is between -1 and 1, the geometric series converges to a over 1 minus r. But if r is greater than or equal to 1, we can say that the series diverges. Okay, so let's look at a few examples and we can have some fun with this. So I'm just going to do some problems. Like number 7 in your textbook. So textbook, page 753, number 7. It says, write out the first few terms and then find the sum. Okay. All right, so we have the sum as n goes from 0 to infinity. Of -1 to the n over 4 to the n. Okay? So let's see. We can write this as when n is 0, that's just going to be 1, right? When n is 1, we're going to get -1/4. When n is 2, we're going to get +1/16. When n is 3, we will get -1. Let's see, 4 cubed is 64. Okay, so that is our pattern. And if we wanted, we could write this as we could see that this is in fact a geometric series where we could let's see, we could write this as I should have thought of this first. I'm sorry. N goes from 1 to infinity. To the n minus 1. 0. We can write it in this form. Do you agree that we could also have written it in this form? Where we put a 1 in, we would get 1 -1/4 to the 0 power, which would be 1. And then when we put a 2 in, we will get negative 1/4 to the 1, which is negative 1/4, and we put a 3 in. Okay. And so I like to write it this way because then it looks just like my geometric series with A. What is A equal to? This is a geometric series with A equal to 1 and R equal to negative 1/4. So the sum is A over 1 minus R, which is 1 over 1 minus negative 1/4, or 1 over, this is 4/4, so that'll be 5/4, or 4/5 is your sum. Okay? All right, let's try another problem. Here's number 8. It says the sum as n goes from 2 to infinity of 1/4 to the n. Okay? So if we write out the terms of this sequence, it would be 1/16 plus, and then 4 cubed is 1/64 plus 1 over 256 plus continuing on in that manner. Now, again, if you want it to be in the form for the geometric series, you can think of it as from 1 to infinity, and then this will be 1 over 4 to the n minus 1. Is that right? Is that going to work? No. We'll need to think of this as I'm sorry, hold on. I guess, I know that it turns out it doesn't matter about the index. I'm just trying to think about the logic of, I guess it's because it's the nth term. Ugh, I'm sorry. Your R, darn, I should have thought of this carefully. It's almost like I need to stop the recording since it's going to be long and ridiculous. If I sit here for a second. No, you do have to, okay. Okay. It would be better for you to figure out your R by looking at, especially if your index doesn't start at 1 and your pattern is not like this, it's better for you to figure out your R by looking at the ratio of these terms as they proceed, because you're for sure always going to be able to, like if you do AR squared divided by AR, you'll get R, right? And if you do AR cubed divided by AR squared, you're going to get R. Does that make sense? So the best way for you to figure out your ratio when you're looking at these is to do like 1 over 64 over 1/16, which is 1/4, right? That's your R. And so then from that, you need to figure out if that's your R, what is your A going to be if you were to re-index this? If you went from 1 to infinity, your R is 1/4 to the n minus 1, and you want the first term to be 1/16, you're going to have to make that 1/16 your A. Does that make sense? And then it fits right exactly into your pattern. Now if I put 1 in, I get 1/16. If I put 2 in, I get 1/64. Okay. And so then S sub n is A over 1 minus R, which will be 1/16 over 1 minus 1/4, which is 1/16 over 1 minus 1/4, which is 3/4. And so then that's going to be 1/12, right? Okay. All right, I'm going to do better. I'm going to get the next one. I'm going to do better. This has got to be just very encouraging for you. All right, let's try here's number 9. The sum as n goes from 1 to infinity of 7 over 4 to the n. Okay? All right, so let's see what the pattern is. This is 7/4 plus, what would the next one be? 7/16 plus 7/64. This seems to be their favorite R. Okay, and so we continue on. So what does it seem like your R is? Your R has to be, what you're going to want to do is if you divide 7/16 by 7/4, you get, again, R is 1/4. Well, if R is 1/4, then what does A have to be? Well, pardon? 7/4. Let's see. If we want to go n from 1 to infinity, and we want this to be R, remember, we want this to be to the n minus 1, right, in the formula. So what does this have to be? When we put 1 in, yeah, we get 0. So, we just get 1 because it's 1/4 to the 0 power. So this is our first term, is the 7/4. That's our A. Okay? So S sub n is equal to A over 1 minus R, which is going to be 7/4 over 1 minus 1/4. And so that is, I think, 7/3. Does that sound right? Okay, I'm doing better. Are y'all doing better? I don't know. I didn't do a very good job explaining that at all. See, then it's like, do I redo the video? Do I stop the video? Do I just let you have to deal with it? I should probably just paint my fingernails. Here's another one. The sum as n goes from 0 to infinity of -1 to the n times 5 over 4 to the n. All right? So let's see if we can see what happens with this one. The first term, when we put 0 in, that'll be 1, and then it'll be 5, right? And the second term, when we put 1 in, will be -5/4, right? And when we put 2 in, it will be 5/16. Is this like the most boring? What's my R, Brandon?
1/4.
I think it's actually going to be -1/4, but otherwise, yeah.
Okay.
This book, they can't think of a better R than 1/4 or -1/4. So R is -1/4. So if we want to put it in the pattern like this, we want this to be to the n minus 1, then our A will have to be 5, right? Okay, so I guess it is, the A is always this first term. It doesn't matter what the index is, A is always the first term. I guess that's what we can conclude from this. Okay, so it's 5 over 1 minus negative 1/4, which is going to be, our answer to this one is just going to be, okay, so this is 4/4, so this is 5/4. When I flip it, the 5's cancel. So I think I'm getting 4 is my answer on number 10. Okay? All right. Let's look at a problem like number 11. How about the sum as n goes from 0 to infinity of 5 over 2 to the n plus 1 over 3 to the n? Okay. Well, what you need to recognize on this one is that you actually can think of this as two geometric series. You can distribute this like this. Okay? And you should be able to see this one is going to have a R of what? R will be equal to what? What do you think? You want to write a few terms out first? Yeah, okay. So it's 5, right, for the first one. And then 5 halves. And then 5 fourths. And then 5 eighths. So 1/2 is your R, and your A is 5, and your R is 1/2. Okay, and then for this one, any guess on the R? Or do you want to do a few? So it would be 1 plus 1/3 plus 1/9. What's that one? 1/3. Yeah. So A is still going to be 1, and R is going to be 1/3. So this is going to be 5 over 1 minus 1/2, which is 10. And then this is 1 over 1 minus 1/3, which is 3 halves, right? And so this is 10 plus 3 halves, which is 11.5 or 23 halves. Okay, so you could actually get it where you have two geometric sums that you're adding together. So that's kind of fun. All right, another type of geometric series that you can get, or not, just another type of series is called the telescoping series. And it's fun because the reason it's fun is because you can look at it and you get to do partial sum. You get to do partial fractions. You remember partial fractions? You thought those were cool. So partial fraction decomposition, right? So here's an example. Say we were asked to find the sum. And it was the sum as n goes from 1 to infinity of 1 over n times n plus 1. Now, if you just started to go at it with this problem, you're going to run into some trouble. I mean, you'll see that the term, what is it going to be, like 1/2 plus, I mean, you may not see the pattern, or you're definitely not going to see the pattern if you just looked at it in its raw form. In its raw form, 1 over n times n plus 1. If we put 1 in, we get 1/2. If we put 2 in, we get 1, let's see, there's a 2 here, a 2 times 3, so that's 1/6. If we put 3 in, that's 3 times 4, that's 1/12. If we put 4n, we get 4 times 5, which is 1/20th, right? And if you looked at this, you would see that it's not geometric. You don't have the same ratio each time, so it's definitely not geometric. And you're wondering, does this converge? And if it converges, what does it converge to? What is the sum of this series? All right, and so it turns out that you can use, it's not completely obvious just looking at it this way, so you may want to use partial fraction decomposition. If you look at 1 over n times n plus 1, and think of it as a over n plus b over n plus 1, right? This is familiar. And so then you say 1 equals a times n plus 1 plus b times n. Then you would have 1 equals a n plus a plus b n. And then this is 1 equals n times a plus b plus a, right? And so you would remember that what has to be true is that a plus b has to equal what? It has to equal 0, and then clearly a has to equal 1, right? Which means that b has to equal -1. So we can write this series, the sum as n goes from 1 to infinity of 1 over n times n plus 1, as the sum as n goes from 1 to infinity of 1 over n minus 1 over n plus 1, right? Now, the beauty of thinking of it in this way is you'll see when you start writing the terms out. If I put 1 in, I'm going to get 1 minus 1/2. When I put 2 in, the second term, it's going to be 1/2 minus 1/3. When I put 3 in, I'm going to have 1/3 minus 1/4. Okay, what do you notice? Do you notice anything? This -1/2 and positive 1/2, when I add them, are going to cancel. -1/3 and positive 1/3, when I add them, are going to cancel. -1/4, and then I'll get a positive 1/4. And so I'm going to end up with, like in general, this will be 1 over, just we could say k, or whatever, where I'm at, minus 1 over k plus 1. But that 1 over k is going to cancel, and so I'm going to be left with 1 minus 1 over k plus 1. And so that is s sub k. And so as k goes to infinity, or you could say n, as k goes to infinity, then this sum, s sub k, is going to go where? To 1. So that is the sum. The series converges, and the sum is 1. So you may find that thinking of these as looking at telescoping series, when you look at them, it's kind of a fun thing to do. So let's try another example. Let's see. Do you guys need a refresher on partial sum? I mean, on partial fractions? Do you want a little bit more complicated one? Or this is a really complicated one. I don't know if I want to do this one. All right, I will. 17. N goes from 1 to infinity. We've got 40n over 2n minus 1 squared times 2n plus 1 squared. Okay, so remember, this is a really complicated one because we've got quadratic factors, but we'll go ahead and do it because you have one like this on your online homework. So this is 40n over 2n minus 1 squared times 2n plus 1 squared. You can think of that. How do you remember? Do you guys remember how to decompose this? Brandon, do you remember? Oh. Do sort of, well, you have to, you're going to have an A, and it's going to be over 2n minus 1. These are linear factors, so you're not going to have the bx and the c. That would only be if you had quadratic, like if it was 2n squared. You know, these are linear, but since they occur twice, you have to account for each time that it occurs. So you have to have a b over 2n minus 1 squared. Does that make sense? So each time it occurs, you have to put a letter in. And then you'll have a c over 2n plus 1 and a d over 2n plus 1 quantity squared.
Just a quick one. What is it that you use like ax plus b?
You use the ax plus b if it only can be factored down to a quadratic that will no longer factor anymore. Like if you got 2x squared plus 4 and then that were squared, then that would be really messy. But you would have to have the ax plus b over 2x squared plus 4 plus cx plus d over 2x plus 4 squared. You know, I mean, it would be really hideous. But yeah, it has the x in it if this factor is quadratic. This factor is linear, though. It just occurs twice, but it's linear. Okay, so this is 40 over n equals, all right, so this is going to need what does a need? Brandon. I'm going to get you the fingernail polish out. What does a need?
Oh, I'm sorry.
I'm just kidding. It's not
I
my
was
day.
texting them to tell them about the MCC website.
Oh, you were telling, because you're so excited.
Yeah.
My picture's on the website.
Okay, what
All
was
right.
the question? I'm sorry.
You better, now you have to tell me what A is. What does A get?
A is...
That's right. I don't think I'm not going to put this on the website too. No, I'm just kidding. A will get, A has a 2n minus 1, right? So remember, this is that common denominator stuff. So it needs another 2n minus 1 because your common denominator is 2n minus 1 squared times 2n plus 1 squared. So all A has is a 2n minus 1. So it's going to need another 2n minus 1. And then it has to have the 2n plus 1 squared. You with me? All right. And then how about B? Can you tell me what B needs, Brandon?
It needs the 2n plus 1.
Right, squared. All right, and then C needs the 2n minus 1 squared and another 2n plus 1, okay? And then D, all it needs is the 2n minus 1 squared. Okay, now, I really don't want to multiply this all out. So I'm going to tell you the answer. All right, it turns out that we get lots. Do you know what to do? I mean, you get the idea. And you multiply it all out, and then you group them together, and then you follow through, and it's actually going to have, it's quite a lot of work, lots of work, but it's just algebra to determine A equals 0, C equals 0, B equals 5, and D equals negative 5. A and C are equal to 0, B equals 5, and D equals negative 5. So if you're, bored later, you can figure that out with your algebra. Well, then why do we do all of that? Well, we do that so that we can then say that since A and C are 0, this series of 40n over 2n minus 1 squared times 2n plus 1 squared can be thought of as, if A and C are 0, it's going to be 5 over 2n minus 1 squared minus 5 over 2n plus 1 squared, right? And that 5, actually, you can factor that out. 1 over 2n minus 1 squared minus 1 over 2n plus 1 squared. And if you were to write out a few terms, you should see that you are going to have that telescoping behavior again. If we put 1 in, we're going to have 2, let's see, that's 2 minus 1, which is 1. So that's going to be 1 minus, if I put 1 in here, it's going to be 3, so 1/9. Plus, when I put 2 in here, I'm going to get 1/9. When I put 2 in here, I'm going to get 2 times 2 is 4, plus 1 is 5, 1/25. And then when I put 3 in here, I'm going to get plus 1/25. And you're starting to see that it's a telescope because it collapses down. And in the end, you're going to have the kth one, you're just going to have 1 over 2k plus 1 squared is going to be left. And the minus 1 will have canceled. So you're going to have 5 times 1, and actually this will be a minus, minus 1 over 2k plus 1 squared. But as k goes to infinity, that's going to go to 0. So your sum is going to go to 5. All right? So that is just some fun that you can have with these problems. That's called a telescoping series. I know, all that work. I mean, would you have thought that necessarily that would go to 5? I mean, to me, series are just such a mystery and sort of an interesting thing to look at. Let's see. There are a couple more at the beginning. Maybe I should do to make sure you're good with your homework. Maybe I should have started with these problems, but they're actually easier once you know about the geometric and the telescoping, then you can kind of work these a little bit better. But if you looked at, this will be more like online homework problems, the first 3, similar to first 3 online homework. Would be like this problem where you are asked to find a formula for the nth partial sum. And now that you know about the geometric and the telescoping, it might be easier for you to do that. Let's see. Okay, here it is. 2 plus 2/3 plus 2/9 plus 2/27 plus 2 over 3 to the n minus 1. Okay? All right, now, you may recognize this as a geometric, right? With r equal to what? What does r look like it is?
One-third.
Yes, r is 1/3. And what do you think a is? 2. So if we want to describe the formula for the nth partial sum then will be S sub n is equal to let's see, 1 actually, what do they want? Find a formula for the nth partial sum of each series and use it to find this. Oh, I'm looking at the wrong, sorry. Looking at the wrong thing. Okay, and so it looks like we can say, in general, S sub n is, remember, a times 1 minus r to the n over 1 minus r. So wherever you are for n, that's your general term. But as n goes to infinity, this part goes to 0. So we can say that if we want to, we can write it like this for when, like say we just wanted the fifth partial sum, we could write it like that. But if we want to know what the sum of the whole series is, the limit as n goes to infinity, we can just say that S sub n is equal to a over 1 minus r, which is 2 over 1 minus 1/3, 2 over 2/3, which is 3. So, like, obviously you're not going to get 3 if n were just, if you just added the first 3 terms, like if you were just going to do S sub 3, you may not get exactly 3. But as n goes to infinity, you do get it. So this formula you can use for at any point that you want to stop, S sub 5, S sub 12, you can get exactly what it is. And this is as n goes to infinity. So that's how you can work those problems. And then there's also one like number 5, where they actually give you same instructions, but they give you a telescoping series. And you can kind of recognize them. And then plus they tell you this is 1 over n plus 1 times n plus 2. You can recognize that as telescoping. And proceed as before. As in the other examples. I'm not going to do it because I'm kind of running out of time, but just want to show you what the only 2 types of series that they're going to throw at you that actually have sums are either going to be geometric or telescoping. So you're not out of the wood. I mean, it's not awful yet. This first section's not too bad. Okay. All right. Now on this theorem, there is Theorem 7. It turns out that if you know the series converges, then the terms of, as n goes to infinity, the term must go to 0. That has to be true. And that should make sense to you, because if it didn't go to 0, say it went to 5, well then you'd be adding 5 infinitely many times, and so the whole thing could not converge. Okay, so that's your first test when because we're going to be asking a lot, does the series converge? This is called the Nth Term Test. And if it doesn't even go, if the Nth term does not converge to 0, you can say right away that the series does not converge. Now, it does not go the other way. Just because the Nth term goes to 0 does not mean necessarily that the series converges. And we'll look in section 11.3 at an example, but the really pretty example is the harmonic series, 1 over n. It actually does not converge, but its nth term does go to 0. But then 1 over n squared, I kind of talked about this before, 1 over n squared does actually converge, and it's like pi squared over 6 is the answer. It took Euler like 73 years to get there, but we could prove that it converged pretty quickly we're going to learn called the integral test. We kind of already looked at it. All right, so this is the nth term test for divergence. You know that it's going to diverge if the nth term fails to exist or is different from 0. If you look at the nth term and as the n goes to infinity, if it doesn't go to 0, then it's just not even worth talking about. You're done. The series does not converge. You have these formulas. If you know that they're both convergent, then you can kind of get into the sum, the difference, and the constant rule. That should make some sense to you. Okay, so let's look at, before we stop, let's look at a few more questions about convergence or divergence. So we will just look at some examples. So these are examples, and the question is, does the series converge or diverge? Converge or diverge. And again, I'm just going to be taking problems from your text. All right, and so let's look at number 23. Here's a series. The series as n goes from 0 to infinity of 1 over the square root of 2 to the nth power. Okay, now when I look at this, personally, I would write it as 1 over square root of 2 plus, or sorry, actually the first term's 1, and then 1 over the square root of 2 plus 1 over the square root of 2 squared, which is 2, plus 1 over the square root of 2 cubed, which is 2 on the square root of 2, plus, you continue the pattern, 0, 1, 2. Okay, so what do you think? Converge or diverge, and why? You only know two things so far. You only know if it's geometric, that it converges, if your R is less than 1, or if you can kind of see that telescoping pattern. Okay? Do you see a geometric pattern? One over the square root of 2 is your R. Okay? Is that all right? I mean, it feels uncomfortable, but it is. 1 over square root of 2 is your R. And so this is a geometric series. R is equal to 1 over square root of 2. A is equal to 1. So since your R is between negative 1 and 1, it will converge to A over 1 minus R, which is going to be 1 over 1 minus 1 over the square root of 2, which is equal to 2 plus the square root of 2 if you do a bunch of work. Okay? I have to, rationalize the denominator and that sort of stuff. All right. Now, let's do another one. How about this problem? The sum as n goes from 0 to infinity of the cosine of n times pi. Well, let's kind of think about what do y'all think is going to happen to that one? Well, if you plug in numbers, you're just going to keep getting numbers. So you might try that nth term test. What is the limit as n goes to infinity of the cosine of n times pi? And remember that n is counting, like it's 1, 2, 3, 4, right? So it's not just like this is going to be cosine pi, cosine 1 pi, cosine 2 pi, cosine 3 pi. What kind of numbers are you going to get? You're either going to get 1 or negative 1, and it depends on whether n is positive. Do you agree that it's negative 1 to the n? Because when n is 1, it's cosine of pi, which is negative 1. N is 2, it's cosine 2 pi, which is negative 1 squared. So it's negative 1 to the n. This is not equal to 0. And so this diverges by the nth term test. Make sense? Okay, good. All right, let's try number 29. The sum as n goes from 0 to infinity of e to the negative 2n. Okay? What do you think that one is? Well, you can think of this as the sum as n goes from 0 to infinity of 1 over e to the 2n. Right? And then this you can think of as 1 over e to the 2 to the n. Yes? Okay. What will this be? That's your R, right? If you started going on it, this is actually going to be a geometric. I mean, you could write some terms out to see it, but hopefully you would get there. And your A is what? And your R is what? R is 1 over e squared. What's A? Good. It's the first term, which if you put 0 in, you get 1. So it sums to, remember, it's A over 1 minus R, so it's going to be 1 over 1 minus 1 over e squared. You're going to common denominator there. It's going to be e squared minus 1 over e squared, and then you're going to flip it. So it's e squared minus 1 over e squared. Okay? All right, so you kind of get the idea there. I'll let you play with some of those. And then let's look at just one more idea, which is this idea of repeating decimals. It turns out that you can write a geometric series, a repeating decimal as a geometric series. So if you took, so if we wanted to write as, so 0.23 repeating as a fraction, what you can do is you can think of that 0.23, 23, 23, 23. You can think of that as (23 hundredths) plus 23 tenths, hundredths, thousandths, 10 thousandths, or hundredths squared, plus 23 tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, millionths, which is 100 cubed, right? And you can see that this is a geometric series, and your R is what? What is your R on that? Well, if you divide this by this, what do you get? So this is a geometric series. Yeah, I won't tell anybody that you had to type that in your calculator. But 23 hundredths divided by 2300 squared divided by 23 hundredths is just 100. That's your R. And your A is the first term, which is 23 hundredths. You okay? All right. And so then the sum is going to be A over 1 minus R, which is 23 hundredths over 1 minus 100th, which is 23 hundredths times, this is going to be 99 hundredths. So this is 100 over 99. And so your answer is 23 over 99. And while you're doing this, if it can reduce, you would. But if you type in 23 over 99 on your calculator, you're going to get that 0.2323 repeating. So that's kind of a cool thing that you can do with geometric series. And I promise this is the last one. I'm sorry it's taking so long. But I want to make sure that I've covered everything. Say it looks like this. Say it's 1.24 1, 2, 3 repeating. All right, what you need to do is you need to figure out what you want to get it to where you're just working with the repeating part. So what you can do is you can think of this as 124 hundredths plus, then this would just be 0.23, 0.123, or sorry, well, let's see. Then you would have it'd be 0.00123, right? Which you could think of as 124 hundredths plus 1, 2, 3 over tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, So that's 123 over 100. Where is it? No, it's my turn to be silly. 1, 2, 3. Actually, just count the number of decimal places. 1, 2, 3, 4, 5. So it's 100, or 10. You can think of it as just 10 to the 5th. And then this is going to repeat again, like this. And so to get the next one, you're going to be, there's 3 decimal places, so it's 10 to the 3rd. So you could do, what would be the best way to think of, I'm rushing, I'm not reasoning this out. Okay. 10 to the 5th, and then this is 6, 7, 8. So it's to the, well, actually you want your R to be 1 over 10 to the 3rd. See if you can feel that for the next one. Because that'll get you to that'll get you 1, 2, 3, 4, 5, 6, 7, 8. That'll get you in the 8th place, right? This gets you in the 5th. This gets you to that one, and then in general, your A is 123 to the 5th, and your R is 1 over 10 to the 3rd. So this is 124 over 100 plus 123, sorry, the sum as n goes from 0 to infinity, or 1, they do 1 to infinity, of 123 over 10 to the 5th times 1 over 10 to the 3rd, and then this is to the n minus 1 power. So that'll get you the first one, the second one, the third one. So this is your R, and this is your A. And so then this will be 124 over 100 plus 123 over 10 to the 5th over 1 minus your R, which is 1 over 10 to the 3rd. And if you work all that out, you should get 41,333 over 33,300. Ugh. Really didn't do a good job on that. Let me see if I can handle the pattern again. If I can, what you have to do is you have to kind of describe, there's actually a pattern to this where you don't have to work, you don't have to think so hard. Since there's 3 repeating decimals, it's going to be 10 to the 3rd is going to be 1 over 10 to the 3rd is your R. When there were 2 repeating decimals, notice that it's really 1 over 10 squared. 100 is 1 over 10 squared. So I probably should have I put it in the hundredths because it felt better. But it's however many repeating decimals it is, that's going to be your exponent for the power of 10. So it's 10 squared, whereas this one was 10 cubed. But to figure out your A, you want to write that first one. First of all, you don't want to have any numbers in front. So you have to get anything that's not part of the repeating off, away from, and that you'll just add that in at the end. But then when you start the pattern, this part will be your A, and then this will be this because it's repeating 3, it's going to be 10 to the 3rd. It's really late. Should we try one more, since I don't know that I did a very good job on that one? Let's try one more, see if we can do it. Here's 58. 3.58 0.142857. All right? Now, you know this is going to be a 3, and then you have 142857, 142857, and you continue that on. So, based on this logic, you're just going to have the 3 plus, this first one is your A, 1, 2, 3, 4, 5, 6. So this is 142857 over 10 to the 6 plus 142857 over 10 to the 6 times 10 to the what? 1, 2, 3, 4. This is it's a bummer. It's also 10 to the 6 because we have repeating. We have 6 repeating. Does that make sense? So this is for the number of repeating. And then, so it was 2 when we had 2 repeating. It was 3 when we had 3 repeating. This one we have 6 repeating, so that was 6. Now this is just one set of the repeating in its correct decimal form. Does that make sense? So this is your A is equal to that. What's your R going to equal? One over 10 to the 6 from that part. And then you still have your 3 plus on the outside. So it's going to be 3 plus this thing over 1 minus R. Right? So it's going to be, I mean, these are not like the most awesome problems in the world. This is like the world's longest video, though. Here, let's try. It keeps repeating. Let's pick one for fun. You're never going to be done with this class. Give me a repeating decimal, Brandon. Let's see if we can do it. Pick one out. Just make one up.
.12345.
Okay, how about just 0.333? 'Cause I want to see if I can get 1/3, and then we'll do your 1, 2, 3, 4, 5. Okay, so 0.3 repeating. Let's see if my logic. I know that this is 1/3. I want to see if my logic is working. Okay, so I can think of this as 0.3 plus, or I can think of this. What did I say? What was my logic? My logic was to write this as 3/10 plus 3/10 times 1 over 10, right? Plus 3/10 times 1 over 10 squared, right? Does that make sense? Will that work? Yeah, because this will get me 300ths and 3,000ths. And if I keep adding them, it's going to be 0.3 forever and ever. So this is A is going to be 3/10, and R is going to be 1/10. And the R is from how many you have. The reason it's 10 to the 1 power is because you just have 1, right? Okay, and then the formula is A over 1 minus R. So 3/10 over 1 minus 1/10. 3/10 over 1, that'll be 9/10, which is, thank goodness, 1/3, right? Okay, now let's do Brandon's. 1, 2, 3, 4, 5. Okay, that's it. That's your repeating decimal. Okay, I'm going to say that this is 1, 2, 3, 4, 5 over 10 to the 5th, because that's the first one. That's the first term. And now to continue that, it's going to be this times 1 over 10 to the what? 10 to the 5th. But that 5 comes from the fact that you're repeating 5 decimals. Okay, so let's see if that's right. Okay, so that would make A this thing, and that would make R this thing. And so this would be A over 1 minus R, which is 1, 2, 3, 4, 5, over 10 to the 5th, over 1 minus 1 over 10 to the 5th. All right, so this is 10 to the 5th minus 1, right? 1, 2, 3. Am I losing you? Did I lose you? I could lose you at any minute. 10 to the fifth minus 1 over, did y'all see the 10 to the fifths are going to cancel, and then that's going to flip up. It's going to be that, right? Are y'all with me?
Sorry, I got distracted for a second.
It's arithmetic now. If I just get a common denominator, this is 10 to the fifth over 10 to the fifth. So this is 10 to the fifth minus 1 over 10 to the fifth, which is going to cancel with that 10 to the fifth. All right, what is 10 to the fifth? 1, 2, 3, 4. Is that 10 squared has 2 zeros, so 10 to the fifth has, so this is 100,000 minus 1. So 1, 2, 3, 4, 5 over 100,000 minus 1, which is 99,999. All right, type that into your calculator. 1, 2, 3, 4, 5 divided by 99999. If you don't get 0.12345, then I'm stopping. Does it work? Yeah.
Yep.
Now, if that isn't, did it work, Brandon? No, you can't make your calculator work.
Calculator.
Is he there? Is it working? Yes?
Yes.
Okay. So, I mean, if that isn't just the most awesome thing you've learned, I mean, now it's like people, you'd be like, just give me a repeating decimal, any repeating decimal, and you can make it a fraction. You're awesome because you can do that now, and it's all thanks to geometric series. And just to encourage you, I will tell you that Becky actually learned how to do this. She's in 7th grade math, and they have a little lesson on figuring out how to do repeating decimals to fractions. But all she does is this little algorithm. She doesn't know the why. You know the why. She just learned a little pattern, because there is a pattern. If you did enough of them, you would see that there is a pattern to it. That whole 999 thing sort of comes up. So if you ever did the UIL number sense test, converting repeating decimals to fractions real quickly in your head was always one of the questions, because there's a pattern if you did enough of them. So go home and make up 20 of them and see if you can find the pattern.